guys, this is a response to Phil to give him, and of all you guys, obviously. But response to Phil here. A good find. That array of large diagonal cracks seen clearly across the end of the walkway could only be caused by massive twisting motion. Okay, let's just go from there. This is what I talk about, the twisting, the torque. Let's show you during the move, and I wrote a beautiful response to Phil. But then magically, when I'm typing, there's two keys I can press at the same time, which I can't figure out what they are. It will delete, copy, delete, select all, and delete all in one shot when I'm typing using, Shift and looking for a capital letter. Something magically happens. Deletes the entire comment. It was beautiful. So that's why I'm now going to do a video response. I'm going to jump around a bit, but just give you the data, and then I'll put it all together. So here's and I'm trying to talk fast. This is the failure area of number 12, and here's 11 up here. 12B sticks out, as I'll keep talking about, in the cantilever. Here's the anchor that was supposed to hold that structure down into the top of the pier. It was never placed there. It was just the pipes there now, the white pipes we see in the OSHA report. This is supposed to be grouted. But now let's go to, scrolling on up. Well, I might just pause the video. Talking about the events now. They did not, come on, I'm trying to make this a fast video, so let me try to speed it up. So the bridge, the torque action is taking place, I believe, at the canopy only, not really at the diaphragm. The diaphragm breaks. But remember, this whole structure has, in the center line of it, the load of the entire canopy. However much, hundreds of thousands of pounds you want to call it, tons rather. It still all lines up down the center of this structure, down the center line, sitting on top of this deck. This deck has post-tensioning down the center line, and does not have it there, but transversely and longitudinally has post-tensioning members. It's supposed to share the loads outwards. Here's two theories I have, two thought processes on the load transfer here. And this is what I started telling Phil. And, all right, so we grabbed the canopy. Let me pause the video. Oh, I guess I don't have to. They jumped to it. So here's that was odd, right? It's right when I was ready to pause the video. So here's the canopy. Here's the design. So just, guys, you remember this was going to have pipes on it, 16-inch pipes. But I want you to remove every last one of these supports. I talked about this in another video. Don't remove number 1, and this is number 12. So see, they're numbered. But remove numbers 2 through 11. And now the deck will all be fully post-tension, and the canopy will have just the 2 post-tension members in it per side at this time. So the post-tensioning, without these supports in the middle, you would post-tension this so no deflection would happen in this deck. You put so much compression on it that the deflection of the dead load won't exhibit itself. It will have no bowing down the center. So you got me on that? There's nothing here to transfer those loads if it did bow. So remove this out and put it there. Now what happens? All the loads, obviously from the canopy still was floating in the air, will have to be down number 1 and number 12. Right here. So here's the end position. Let's call this the end position of number 12, 1 foot 9 inches. So the span, so look at over here where my mouse is. So this has to be center line. Now imagine what happens if you could just take your hand now, keep the center line, and just push this to the right a little bit. If you were to push this to the right, this would create a lot of torque down here, wouldn't it? Right down here, causing this to fail here. Now with no supports down the middle. Now, let's just say the post-tensioning is not enough, and the reinforcement is not enough to keep this 16-foot span here. See 16 foot? The butterfly type deck or canopy, umbrella, I like to refer to it as, but I'm going to call it butterfly now because it wings up. 16 foot wide, all transfers down the center line of this, one way or another, these loads are transferring to this diaphragm or into the deck, partially into the deck area here, and then out into the diaphragm, but never like a truss system. Not like a truss system. This is post-tensioning. It is not designed to, it's designed to keep things in compression. So it's not designed to be actively going in and out with like a truss system would. So that it's always designed with all this load in mind with the steel pipes. Now they already concreted that in and grouted it in as reported by OSHA. Of course, I saw no signs of grout, but they've already grouted it in. Let's go with that. So this is locked in time. It's done. There will be no more going back and repost tension. If you grout it, it's now locked in, literally locked in around the concrete there. Friction is going to help hold it together. It's going to make this act as one, more so also. But, you know, it's so the concrete's in compression, but not the grout. All right, so just so you know, the grout's not in compression because the grout is out afterwards. The grout can go in compression if something starts failing. Then the cables will start, you know, taking over. It might put the grout in compression. So we have the what's in compression is everything around the grout, but not the grout. So follow that because it's already, you know, it's around the tight member. All right, so I hope you can follow that. So I'm not trying to add anything to that yet. So now you have this, the cracks are down here in the diaphragm. They left off the diaphragm for clarity's sake in this part of the drawing. But the cracks come this direction all the way down through the diaphragm, which is down here somewhere, and this direction also down here. But on the base of that diaphragm, we see the tape measuring from the OSHA report showing approximately 5 inches on this side and maybe 3 inches on this side of it separating and dropping down. That shows it's no longer in plane, and the only way to get this dropping down and that coming up, and that raising up, is you'd have to torque the entire 12. 12 is tied at the canopy, though. So, therefore, the canopy had to take a torque. Now, I'm not saying the entire canopy took the torque all the way down to the end. Well, theoretically, it took some torque. It tapers off, right? But I'm saying all the torque happened in this triangle right here. That when they had the bridge in the, as Denny Page says, hey, we don't know why the cracks happened, but we can say it wasn't doing anything over there in the staging area. Well, the staging area had a different setup, as we know. It had cross bracing of some type at the diaphragm, though. It was not cross bracing at the canopy. The diaphragm, as in the OSHA report shows, it's in the cross bracing is in the diaphragm, not in the canopy. Nothing keeping this stable besides the 1'9" and the forces of post tensioning down here, down all of these clamp force, creating a clamp force that allows it not to topple over. 4 members are inside here, 2 in here, and so on and so on. 9, I think, had nothing, but 4, it keeps it in balance. It's legs of this thing, but all down the middle, there's 16. Now, theoretically, if it's all balanced, well, then the loads come out to the disbalanced. But let's get back to how I was, and this was all I was writing to Phil. If we take these out, would this deflect on its own? Well, theoretically, it doesn't per the plans, or they would have said, wait a minute, you're getting deflection in this diaphragm and the canopy. The loads are now coming down these members here, wherever they are, and you're now point loading all this deck. I'm thinking that this was not designed, so 2 thoughts. It was not designed to be point loaded. It was designed to carry the loads down, not designed to be point loaded down here, well, very insignificantly so. And, well, maybe, it's a maybe part, because I'm going to do 2 things here. Let's say it was mostly designed to go down number 3 here, number 1 and number 12, the loads of the canopy. But we have the loads, also the steel pipes. It's huge, isn't it? So that would make me think that, well, logically, that the deck was going to participate to quite some degree of transferring these loads in this nodal area, if you will, out into the longitudinal post-tension cables and then into the diaphragm. This number 11 that they've tensioned and detensioned acts as a diaphragm. I like to consider it, the back of here. It's a trumpet area. This trumpet area is very weak in design because it has, well, we know how you can see how it failed. It's obviously weak in design. It's blistered. It only has so much footage on inches on each side of it. This guy right here, and part of it, the torque action can just simply be this one's out here, this one's here. This one's pulling more than that one, but theoretically they have them both pulling at the same. One being just a little bit longer, and they have them loaded the same nevertheless. One's being loaded like a 1/2 inch more. and maybe it's this from the number B. This is A and B as far as I know. B is the big failure. So this also, so this is a diaphragm area for the post-tensioning up here, and it's supposed to have been grouted as we talked about. So when they detension number 11B, I'm more concerned about 11B, not so much about 11A, B here. This allowed this diaphragm they detensioned it to go downwards. The clamp force went downwards because there's so much load coming down 12. As Denny Page states, it's like 950 kips coming down here. So 950,000 pounds of force coming down here, and nothing to keep it holding on the deck anymore on this little lip, besides this partial section here, and then the cantilever. But Denny Pate said if it was shimmed here, is what he's saying, the loads would have transferred down to the pier. Because it was not shimmed, it allowed the loads to create a shear in the back of the diaphragm there. And it cracked like hell. But here's the thing, he states that he doesn't know how it cracked, or why it cracked, but yet his theoretical retensioning sounds like he does know how it cracked. I'm saying that he's playing a little mousy, perhaps, and he was trying to put this thing back into here. But I don't know if they ever, with a 1 hour meeting, if they ever got a true baseline of this deck, if it was really still in plane. This is so critical to me. Was this deck in plane, and was the canopy in plane? But number one, is the deck in plane? Was it flat? Was it flat? Did it have any dips in it? Any at all, specifically from here to here? But you wouldn't be able to tell that just from running a string to there. You'd run it from there to the other end of the structure. Just a string, for example. But 175 feet, you're not going to get that tight enough. You're going to use your survey equipment and get that true reading, and it would be so easy to do. But yet, all these people out there, and nobody's got survey equipment to look at that. I mean, it would have been so easy to do. So this stayed the distance when we see the collapse. This never separated in the air. What separated is here and here. So how do we get the separation here and here? Again, cause this triangle right here to fail. That if we just kick 12 being a non-force member, some people believe, some clowns believe it's a non-force member. Well, if you remove it from the factor there, what holds up the rest of this diaphragm? Just this cantilever? This would be cantilevering from here to here if 12 is no longer functional. And the compression would still take place. Would that call it a hogging or a bending, bowing inside here, one way up or down? Neutral axis, it shouldn't do anything besides possibly, well, it wasn't designed to be carrying an overhang like that, cantilever from here to here. So that load is going down 12, and Denny Pate reports it as 950 kips. Apparently, that's my understanding from the drawings, from the meeting. So now we have, this, in other words, has load on it. They don't know how it happened, but they knew that put back number 11. So as I was saying to my man here, Phil, as I was saying to Phil here, is that the detensioning lost the racking of this. Detensioning of 11 and number 2 threw this whole structure out of racking, out of its clamp force. Remember, it looks kind of funky. It looks like this. And that number 11 participated in keeping this thing all tight together and from twisting and torquing and falling over. If you look at number 10, here are the post-tensioning in these members. Number 2, that's no longer applicable because they removed it, and number 11 when the failures happened. And then this one section of the failures. Remember, this bridge was failing in the staging area. Cracks presented. This thing was always trying to find equilibrium. And this equilibrium presented itself with the cracks that it was trying, that it in the staging area, that it came to a stop with however the cracks presented. That was the new equilibrium once they removed the false works from here. And once they added under tensioning, and once whatever time took place, whatever cracks you see, that equilibrium was established without a dead load, with just dead load, without any live loads on it. It would have putting live loads on it would have been another game changer altogether. Now, here's number 5, and number 7, 8, 6, everything but 9. 9 has no 9 has no post-tensioning bars in it. So if it was going to also start deflecting, it could have picked here and also here. Look, there's nothing keeping these two to get from this, and this. There's nothing keeping these together besides just everywhere else is post-tensioning too. But in this entire span, you now have another weak point, number 9. So at the time of detensioning, number 12, number 11, number 9, and number 1, correction, number 2, had the same profile, if you will. They had no tensioning in them. Except for when they detensioned number 11, it cracked like hell. That cracked like hell, and then stopping, no longer cracking, continuing cracking away. It looks like it's a temporary crack, right? Like, oh, okay, it's found its equilibrium. No, I state that B reclamped at that point. If this was only loose, it reclamped and saved the structure from its wanting to find more equilibrium. Ultimately failure at that point, I think. I think number 11 gave it its equilibrium. And so that its new form of equilibrium once they detension it. And number 2, it's so substantial. And the loads down here are, the post-tensioning, as I talked about in other videos, it's weaker down this section than down here. And when you longitudinal post-tension cables, the clamp force is weaker down this end than there, as per the drawings as you can find. And I talk about in other videos in that. If you doubt, then I'll direct you to my video on that if you ask questions. But as this detension, this clamp force held this together here and here, never allowing it to deflect here, here, or here. Deflection was here, and here, ultimately, we see in the failure. And that's because it no longer was able to carry, it was always bowing. And that presented itself, the initial cracks we saw were here. That opening right there, it was before detensioning, okay? This is critical. Before detensioning, we saw openings here, cracks here. That's indicative of the only way to get an opening crack is you got to move things apart from each other. You have to move things apart from each other. And the clamp force was present at that point. There was not any sliding going on as the OSHA report talks about. But yet we had a crack here. OSHA report doesn't talk about specifically this crack, how it came apart, how it developed. So that indicates to me, and that was before they detention, remember, that this thing was bowing in the middle to begin with, that it had an amount of creep already taken place, and no surveyor has been found to show that they surveyed this stuff to show that deflection. So I'm saying that this whole thing deflected. During that deflection, that little bit of deflection, that puts more clamp force down here. In theory, this gets looser, more loose, and this pushes out here. And the same thing here also. So I'm double dipping on you. In other words, I'm double dipping on you if you get some deflection here, that your clamp force increases and or decreases, depending on how where the torque action is, where the torque action is, where the moment's taking place. So all of the bending here, this would probably still stay because the concrete keeping its spacer, if you will, acting as a spacer, keeps everything apart from each other. It resolves itself down here on the ends. These being, I got to cut this video short, I know. These acting as all permanent concrete spacers, resolves itself by showing the crack here, and they don't know why, and they just keep moving on. They ignore it. And when they do the detensioning, this allowed that shearing, the shearing to happen in the back of their loads to transfer down, no longer having a clamp force to keep this triangle right here structurally sound. They attempt to recapture it. The triangle fails down at this section. This no longer can take the load, transferring the loads down. Since it no longer transfers the loads down, it transfers mostly down 10. 10 can't transfer the load all the way out to the diaphragm because of the post-tensioning longitudinal cables can't do that. Why again? Because we can stem it, because we have a torque action going on. I just couldn't explain the full failure there. Now I think I really love the torque action because we have this sheared here, this shearing here and shearing here. This came down, and then we see it lift up because it's bowing now in the middle of the deck. That gives us a demonstration of why, explains why the tape measures are higher here, and when you take the tape measure readings off the deck there, and then at the bottom of the diaphragm where they take tape measure readings. Explains approximately 3 inches over here and 5 inches over here, showing that this deck, to do that, this canopy from 10, not the whole canopy, not the whole deck, did a rotation. Right here did a rotation. And let me go small on that. This did a rotation to do that. Doing that, it created a torque here in the diaphragm. And the canopy, putting a torque action inside this first nodal area. That first nodal area being number 10, receiving the forces 10 at the deck. So if we can pretend like this is 10, that we're looking at the base of 10 now, not the end. If you were to rotate, if you were to try to torque 10 by raising one up and one down, you want it pushing the post-tensioning in that deck. There's the transverse and longitudinal cables. You want to no longer transferring them evenly across there as a dead load. You put a torque in those cables, so you have the end of, I'm going to find you so it's the back of the diaphragm, the real end of the failed. And we have those, what I call shear cracks coming here and here. That's my explanation, not punching. And, well, interesting. Shear cracks, no, that's just shear coming down here. So now we got shear here. That rotation again, because this is higher on this end than there. Remember, we have 5-inch tape measure approximately right here. So we have a 5 inch, we have it going up. And down here we have 3 inches. And this total spacing is the total spacing that it should have been. Let me get that for you. Oh, let's finish this and I'll get you total spacing. So then we get this rotation going on. That no longer has these post-tension D1s balanced. You have one side pushing down and one side pulling up. So the post-tensioning now is experiencing a force in a downward force and an upward force, a rotation, a torque. That changes the whole profile of this. The longitudinal cables, the transverse cables are no longer acting as designed, as taking a dead straight load. They're now receiving a torque action. Now, this was designed to take wind and things like that. But it was supposed to be stable with no rotation happening, and rotation has happened at this point. Let me pause the video and find you that spacing. So here's another one. There's 1 through 6. And again, D1s are weaker. Same strength, but they have a maximum capacity failure that will happen sooner than D2 out to here. This is a bundle of 6, and this is a bundle of 12, whatever it may be. This bundle fails first, and not these guys. Once this bundle is overloaded, it's no longer elastic. It's done. It's done. It's no longer functional. And so that torque action just throws this whole thing off, especially the torque action. Let me get you that spacing. Bear with me. So let me address the torque action. We're using C1 and C2. These were post-tension at the time of failure. C1s and C2s. That would be all 4 of these, if I recall correctly. The deck has still got concrete in it, so it didn't create torque action by this being more torque than that one. All that would do is create more compression on one side of the canopy than the other, but it wouldn't create a torque action. It would create an imbalance of the post-tensioning, but not a torque action. So the torque action has to be the weight of this at some point compared to how it's anchored down number 12. So the left side and the right side not being in uniform. Weight distribution at the diaphragm. I mean, between number 10, between 9-10 connection at the canopy and number 12. At that point, this 16-foot wide structure is not balanced. Enough so that it creates a torque action, I think, on the right side of this. When they detension, the right side is the heavier side because it lifts up the left side more so. I got that correct. I might have to adjust that, but I think that's how I'm seeing it now. And further, let's look at it from the top view. And this is the backspan, but we're using this because it has the same similar cantilever, back of 12, sticking off the deck, if you will. So this is looking a bird's eye view down, if you allow me to do that. And we're looking downwards off the back of the deck of the failed section, let's call it. That it could also be a flip of a coin, that when it was detention number 12, that when it dropped down, when it lost its clamp force, it was a flip of a coin, left or right. You know, it could be as simple as that. Or when they were detensioning, the bars had a torque in them themselves. That number, so the bars are this direction, right? Number 11. And when they were detention, 1 and 1, 1 and 1, that the one detensioning in that series created a torque action to help it rotate to one side or the other. You know, that would give you that would also create the imbalance I talk about, where it drops, where the measurements are there. It's not fake imbalance. It's there. So I'm taking liberty because I believe this is not the failed end, but I'm going to work with this failed end, this end anyway. The failed end, I believe, is down here. I guess we can do that. We'll use the failed end down here. So here's the failed end, bottom right here. Let's see if I can get you guys zoomed in. And I believe, whoa. All right, here's your first support. This is and right about here is where the failure happens. That's that torque action I speak of, the canopy rotating, twisting, and causing the torque action down here, down number 10. Causing that torque action that throws us all in imbalance where it can't transfer the loads out to the diaphragm right here. Where it can't cause it. And remember, the load's going down 10 because number 12 has failed. It's failed because it wasn't supported and is a bad blister cantilever, I call it, because it needs support underneath of it in the form of shims. So while I'm here, I might as well show you D1. Again, 12 by 12 strands, and the D2 through D6 had 19 strand bundles. You see the lengths are all the same, so no harm, no foul there. But this means that this would fail sooner. As you can see, it appears the stressing forces in tendons number D2 are 527 kips, and the stressing forces D2 through D6 are 835. Don't get excited yet. The percentages, so this would fail at the same percent as together, equally, if you will, except for these would fail a little later. Let's say that they're all post-tension at 80%. So this would fail when it gets 100, whatever percent it fails at, minimum 100%, 100%, and it might fail a little bit greater than that. At that point, it's no longer functional. It's no longer having a clamp force that you would need, that it can perform anymore. And now these guys would be somewhere. Let's see. So they would be 20%. So if that's 80. They're all at 80. These guys would then just be up in capacity with their forces. They would be equal. Yeah, I got to do the math again. I forget what I did. I think this fails roughly somewhere about 700 and something kips. All right, so look, when they release the live end and dead end, do you see that? This is the live end is 471 kips. It's the failed end of the structure. On the other end of the structure, the clamp force is much greater. Same thing with these guys. The clamp force down there are totally different. So don't let anybody tell you the two ends of the structure are the same. The clamp force on that end of the bridge that failed, it's weaker than the other end. All right, now let's go to all the post-tension bars are the same. Let me jump off of that. All right, guys, sorry, I got to go. Can't finish any more of this video. I was just going to post it like this. Hopefully that gives you an idea about the torque, everything else that we talked about. Thanks. Thumbs up or thumbs down. Tell me how bad I did.